Assalamu alaikum dear students. I welcome you to 25th lecture of probability and stochastic processes. In couple of previous lectures, we have been analyzing the joint behavior of two derived random variables u and v, which assume their values based on the values attained by two underlying random variables x and y, and two transforming functions which define how u and v take their values based on the values of x and y, where u and v are called derived random variables, x and y are called underlying random variables. We analyze the joint behavior of u and v through processing of joint PDF of u and v, which we derived by properly processing the joint PDF of x and y and making use of the two transforming functions which define u and v in terms of x and y. The route that we followed to find the joint PDF of u and v was that we first found the joint CDF of u and v, because CDF, cumulative distribution function, is a family of parameterized events and their probabilities. By finding the joint CDF first, we were able to differentiate it twice using partial differentiation with respect to u and v, the two parameters of the joint CDF, to get a joint PDF which was again a function of small u and small v, which are the two parameters that define the points on UV plane where joint PDF of u and v is defined. Once a joint PDF of u and v is there, we can define events in terms of u and v and find the appropriate region of UV plane where these events are represented, and then integrate the joint PDF of u and v over that region to find the probability of event of our interest. We analyzed the problem of two television sets manufactured by two different manufacturers, and we modeled their service time with random variables x and y. These are our underlying random variables, and from these underlying random variables we defined two derived random variables u and v, where u was, in first example, difference of two service times, and in second example it was ratio of two service times, and v, the other derived random variable in both examples, was the sum of two service times. In first example, we try to answer question like this, that what is the probability that sum of the two service times is greater than 50 months, and the difference between two service times lies between -6 and +6. In the second example, where u was defined as ratio of two service times, we try to answer question like this, that what is the probability that sum of two service times is greater than 50 months, but the ratio of two service times lies between 0.5 and 2. By working with derived random variables, we were able to answer questions which were more interesting and more meaningful. So that's the whole idea behind working with derived random variables, because they allow you to investigate the quantities which are not directly observed but which are functions of observed values of underlying random variables. The process through which we were able to find the joint PDF of two derived random variable was using the joint CDF to reach to joint PDF. Today we are going to introduce a new method to find the joint PDF of two derived random variables u and v from the joint PDF of two underlying random variables x and y kind of directly without going through the joint CDF of u and v. It's not a direct method. You have to manipulate the joint PDF of x and y, and you have to make use of the two transforming functions which define u and v in terms of x and y. In previous couple of lectures, we worked with a couple of examples where we found the joint PDF of u and v from joint PDF of x and y and making use of two transforming functions. You must have noticed that there is some relationship between the region of xy plane where joint PDF of x and y is defined and the region of uv plane where the joint PDF of u and v is defined. If you recall the first example where u was y minus x and v was x plus y, the region over which the joint PDF of x and y was defined was the first quadrant, and region over which the joint PDF of u and v was defined was a rotated first quadrant by 45 degrees, a region which was subset of first and second quadrant, and it lied between a line with slope of 45 degrees and a line with slope of 135 degrees. Similarly, for the second example where u was y over x, the region where joint PDF of x and y and u and v were defined was the same. It was the first quadrant of the plane, first quadrant of xy plane for joint PDF of x and y, and first quadrant of uv plane for joint PDF of u and v. Similarly, there is some relationship between the shape, orientation and location of the regions which correspond to our events of interest. For example, in the first example, the region of xy plane which corresponded to our event of interest was a narrow strip along the 45 degree line, and that was on xy plane. And when we transformed the problem to uv plane where the joint PDF of u and v was defined, then this event corresponded to a vertical strip on uv plane. For the second example where u was defined as ratio of two service times, that is u was equal to y over x, the region of interest on xy plane was a truncated fan. It was a region which increased its width as we moved away from the origin, and the region closer to origin was truncated. But this event, when moved to uv plane, again became a rectangular vertical strip. So depending upon the two transforming functions g, which defines u in terms of x and y, and h, which defines v in terms of x and y, the shape, location and orientation of different events gets transformed from xy plane to uv plane. Today we are going to exploit this relationship particularly for the case of simple transforming functions and come up with a methodology to directly find the joint PDF of u and v from joint PDF of x and y and making use of these transforming functions g and h. When these transforming functions g and h are simple, then this methodology is very easy to work with, where we make use of these simple transforming functions, the joint PDF of x and y, and we get the joint PDF of u and v. When I say simple functions, I mean invertible functions. There is one-to-one mapping between a point on uv plane and a point on xy plane. If there is a point x comma y and two transforming functions g and h, take this point and give you two coordinates u and v, where u comes from g, which takes values of x and y, combine them and give you u. And then there is another function h which combines values of x and y and give you v. So x comma y, a point on two-dimensional xy plane, gets mapped to a point u comma v, a point on two-dimensional uv plane. Then if these mappings are invertible, then there must be a pair of mappings, say phi and psi, which take this point u comma v, combine the values of u and v, and give you a point x comma y, which is the original point. That is, if phi is the mapping which takes points in the uv plane and give you a point x, and psi is a mapping, a function which takes points u comma v from uv plane and give you the y coordinate in xy plane, then these pairs of mappings g and h and phi and psi should be inverse of each other. This pair g and h takes a point x comma y and maps it to point u comma v. Then this other pair phi and psi takes this point and maps it back to original point x comma y in xy plane. So there is one-to-one correspondence between points on xy plane and points on uv plane. So if these mappings g, h, phi and psi are invertible, we have an easy problem to solve. But we can still apply these techniques if these mappings are non-invertible. Please note that we are transforming x and y, the underlying random variables, to u and v, the derived random variables. So it is okay for g and h to be the kind of mappings which map more than one points to a single point. Then you can find the probability of regions around that point which have been mapped from x and y using more than one points. In that case, the probability of more than one points in x and y plane get combined on one point in uv plane. So the mappings g and h from xy plane to uv plane can be many to one, and inverse mappings from uv plane to xy plane does not have to be functions. They can be multiple functions which take care of individual reverse maps. In previous lectures, we have been using the joint CDF to reach the joint PDF. We followed that approach because CDF gives us a parameterized family of events and their probabilities, whereas PDF, the probability density function, does not have a direct interpretation in terms of probabilities of events. PDF or joint PDF is a relative likelihood of different points compared to each other. And if you want to find probability of an event, then you have to integrate the PDF over all the points which represent that event. We are going to use the invertible g and h and phi and psi transforming functions, and this knowledge that if we integrate the joint PDF over a small region on xy plane or uv plane, we get probability of that event, which is represented by all the points in that small region. Let's have a look at such a small region on uv plane and see how the probability of the event represented by this region can be used to find the joint PDF of u and v from joint PDF of x and y. On your screen you can see that this is uv plane, this is the u-axis, and that is the v-axis. On that uv plane there is a small rectangular region with 4 corner points P1, P2, P3 and P4. The point P1 is at a certain point u comma v. Remember, this is u-axis, that is v-axis, and this is a certain value of u, a certain value of v, which represents the point P1. The width of this rectangular region is du, very small number. Du is effectively so smaller than 1 that you can ignore its higher powers. Suppose du is 0.01, and if you take du whole square, it will be 0.001, and du whole cube will be 1/1,000,000th of 1. Actually, you can take du to be even smaller than 0.01, so that the second power and higher powers are negligible. So du is a small width, and this point P2 is u plus du. V does not change. Vertically, this point is same as P2. Similarly, P3 point is at u comma v plus dv. dv is this height, which again is much smaller than 1. So this rectangular region is bounded by 4 points u comma v, u plus du comma v, u comma v plus dv, and u plus du comma v plus dv. So what's the probability of the event represented by this region? Usually the joint PDF of u and v is a varying height function. Over plane uv, the height of joint PDF fuv of u comma v is a function which varies its height. But this region is so small that we can assume that over this region the height of joint PDF of u and v remains the same. It is same as it is the value of joint PDF at point P1, which is u comma v. So if the height of PDF is same and you know the dimensions of this small region, it's very easy to find the probability of this event, which comes out to be the value of joint PDF at u comma v times the area of this region, because you want to find the volume of that sand hill over this small region. Area of that region is du times dv, and height is fuv, the value of joint PDF at point P1, which is u comma v. So probability of this event is value of joint PDF at u comma v multiplied by du multiplied by dv. Now the question is, which is the region of xy plane which gets mapped to this rectangular region under the influence of two transforming functions g and h? We are assuming one-to-one mapping between xy plane and uv plane. Hence, to find that region of xy plane which gets mapped to this rectangular region on uv plane, you can make use of the reverse mappings, the phi and psi. You can use the reverse mappings to find the coordinates of the mapped points on xy plane, which are reverse images of points P1, P2, P3 and P4. So the reverse images of these 4 points will be 4 corner points of the region on xy plane, which is to be used for integrating the joint PDF of x and y to find the probability of this event, which should be the same. The probability as found from the integration of joint PDF of u and v over this rectangular region should be same as integration of reverse mapped region on xy plane and integration over that region of joint PDF of x and y. So let's have a look at that region which is in xy plane, which gets mapped through reverse mappings which are phi and psi. To get to the region of xy plane, which is the reverse map of this rectangular region on UV plane, we will use the reverse mapping functions phi and psi. So if you want to find the reverse image of point P1, which we can call Q1, then to find the x coordinate of point Q1, you will use the two coordinates u and v of point P1 and feed it to phi. So phi is a mapping which takes u and v and give you x. Similarly, psi is a mapping which takes u and v and give you y. So this is a assumed region on xy plane which is the reverse map of that rectangular region. This point Q1 has coordinates of say x1, y1. So x1 is obtained by using the coordinates of point P1 and the reverse mapping function phi. Similarly, the y coordinate of this point Q1 is obtained by using the coordinates of point P1 u comma v and the reverse mapping function psi. Similarly, this point Q2 on xy plane is the reverse map of point P2. Point Q3 is reverse map of point P3 and point Q4 is reverse map of point P4. So in general, a rectangular region in UV plane, which is the event of interest, a very small event with very small area, such small area that over this area the joint PDF of u and v remains almost constant, gets mapped to xy plane through reverse mapping functions phi and psi and give us a quadrilateral, a parallelogram, or a similar region with four corners and edges which could be straight or possibly curved if the transforming functions are not linear. Now the question is, how do you find coordinates of points Q1, Q2, Q3 and Q4 from points P1, P2, P3, P4 and the two reverse mapping functions phi and psi? As we already discussed, this rectangular region on UV plane is very small. Its width is du, which is much less than 1. Its height is dv, which is also much less than 1. We know that point P1 gets reverse mapped to point Q1, and you know the reverse mapping functions phi and psi. So Q1 and P1 get mapped to each other, and with this information we can be sure that point Q2, Q3 and Q4 are going to be close to point Q1, because on UV plane the points P2, P3 and P4 are very close to point P1. We will use a concept which is a two-dimensional extension of Taylor series, where you want to find the value of a function at a point where the value is unknown in terms of the value of a function on a nearby point where the value is known and the first derivative of the function near that point where the value is known. Let's review this one-dimensional Taylor series to get a good idea of how we can find value of a function at a point where its value is not known in terms of a nearby point where value of the function is known. On your screen you can see a function of one variable x. This is the independent axis x, and that's the y which represents the value of the function. This is the graph of the function in question. The value of this graph at this point x is known and the value is y. But we want to find the value of this function at this point, which is close to x, a nearby point. The distance is du, which is much less than 1. So this point is x plus dx, and we want to find the value of the function at this point, which is this value. But we will approximate this value by taking a tangent at this point where the value of the function is known and the first derivative of the function is known. First derivative is the function with slope that is exactly equal to this tangent line. So there is a triangle from this point to that point to this point. And we will assume that the value of the function is not this, but this. And in that case, the value comes out to be this height plus this height. This height is y. What is this height? From this tangent line, which has a slope which is equal to the derivative of the function at this point, this height comes out to be that slope multiplied by this distance du. Why? Because slope of a triangle is the vertical distance divided by the horizontal distance. So slope, the derivative, is equal to this difference in heights divided by this. So if you add this to this y, you will get this height, which is the upper corner of the triangle. And this is very close to the actual value of the function. And if you make this dx even smaller, the difference between the point on this straight line and the point on this function becomes even smaller. So this is the basic idea behind the Taylor series, where we say that the value of a function at a point x plus dx is equal to value of the function at point x plus dx times the derivative of the function at point x. And we can extend this idea to two-dimensional surfaces, where if we are going along one coordinate axis, we will take partial derivative with respect to that coordinate axis. And if we are moving along other coordinate axis, we'll take partial derivative with respect to the other coordinate axis, and we will assume that the points are close to each other, du and dv are small, hence the value at a nearby point can be approximated in terms of value at a point where it is known plus the distance horizontal du or dv and the value of the partial derivative with respect to u or v, whichever is applicable. So assuming that point P1, which is in UV plane, gets mapped to point Q1 in XY plane through the pair of reverse mappings phi and psi. And let's assume that coordinates of this point Q1 are known and they are x, y. Now, the coordinates of other points in XY plane can be found by using this methodology of using Taylor series to approximate the change in functions phi and psi when we move from point P1 to P2, P1 to P3 or P1 to P4, and corresponding movements in XY plane where we move from Q1 to Q2, Q1 to Q3 or Q1 to Q4. Let's see how this can be accomplished. So we have said this point Q1 on XY plane has coordinates which are x, y, and they are known. So what will be the coordinates of point Q2? Remember, this Q2 is inverse image of point P2, which was obtained by horizontal movement on u-axis, and the movement was only du, which was much smaller than 1. So the x and y coordinates of point P2 will be determined by a small movement along u-axis multiplied by partial derivatives of phi and psi with respect to u, because in this movement from P1 to P2 only u changed. So coordinates of Q2 will be x1 plus partial derivative of phi with respect to u multiplied by du. And y coordinate of this point Q2 will be coordinate y plus partial derivative of psi with respect to u multiplied by du. Similarly, the coordinates of point Q3 will be obtained by noting that point P3 was obtained from point P1 by addition of dV. So only V changed when we moved from P1 to P3. Hence, when we move from Q1 to Q3, the change in coordinates from x comma y to a new value will be x plus partial derivative with respect to V of phi and psi multiplied by du and dV, whichever is applicable. Actually, in this case, only dV is applicable. And finally, for point Q4, which was obtained from point Q1 by double movement of point P1 to P4 through small movement along u-axis followed by small movement along v-axis. Hence, the coordinates of Q4 will be slightly complicated because they will involve both movements and both partial derivatives, but they are given in your handouts or any other good textbook, so you can consult that. The point is, if this coordinate is x comma y, coordinates of this point and this point are easier to find by relying on an extension of Taylor series, where we take partial derivatives and multiply them with the movement on the UV plane. Now that we have established that if we know the reverse mapping functions phi and psi and their partial derivatives with respect to u and v, then we can find the coordinates of points q1, q2, q3 in terms of coordinates of point q1, which is x comma y and assumed to be known, and the multiplication of partial derivatives and the movements du and dv. Now, what is the probability of this event on xy plane? Please note that if these reverse mapping functions are linear, then the shape of this reverse mapped region will be a parallelogram. Actually, even if these mappings are not linear, the region is so small on UV plane and of course on XY plane that we can assume that these 4 points Q1, Q2, Q3 and Q4 form a parallelogram. Now the probability of this event as found on XY plane is the integration of joint PDF of x and y over this parallelogram. Once again, we will make an assumption that we made in the case of UV plane, that the region is so small that joint PDF of UV, which is a varying height function, remains of the same height on that region with width du and height dv. So, even though the joint PDF of x and y is a varying height function, we'll assume that over this parallelogram bounded by points q1, q2, q3 and q4, the height of joint PDF of x and y remains the same as its value on point q1, which has coordinates of x comma y. So what's the probability? It is the multiplication of the value of joint probability of x and y at point q1 times the area of that parallelogram. Now the question is, what is the area of a parallelogram with 4 known points? You need to recall your knowledge of vectors, their cross products and the interpretation of the cross product as the area of a parallelogram. On your screen you can see such a simple parallelogram where this vector along the x-axis is A and this vector is B, and the angle between the two vectors is theta. Then area of this parallelogram is length of A multiplied by length of B multiplied by sine of this angle theta. Please note that if this angle was pi by 2 or 90 degrees, then its sine would be 1, and then this parallelogram will be a rectangle, and area of a rectangle is this length multiplied by this length multiplied by sine of 90, which is 1, which is a well-known formula for area of a rectangle. But if you know the coordinates of this vector and coordinate of this vector, you can form their cross product, and the cross product is a vector which is in the plane which is perpendicular to the plane of this, which is parallel to a line which is perpendicular to the plane where these two vectors lie. So cross product of A and B will be pointing out, and cross product of B and A will be pointing in. But if we take the magnitude of that vector which is the cross product, it is exactly equal to the area of this parallelogram bounded by vector A and B. Let's apply this process to the small parallelogram defined by points Q1, Q2, Q3 and Q4. Effectively, we don't need point Q4. Our first vector will be from point Q1 to Q2. Second vector will be from point Q1 to Q3. We'll take these vectors, we'll take their cross product, take the magnitude of that cross product, and that will be the area of that parallelogram bounded by point Q1, Q2, Q3 and Q4. Once we have found the area of the parallelogram bounded by points Q1, Q2, Q3 and Q4, we can multiply that area with the value of joint PDF of x and y at point Q1, and we'll get the probability of the event which was mapped from UV plane to XY plane through partial derivatives of phi and psi using the expanded version of Taylor series. So what are the two vectors that we should use for this cross product? The first vector is from point Q1 to Q2. Let's call this vector A. This vector A is the difference of coordinates of point Q2 and Q1. So we subtract the coordinates of Q1 from coordinates of Q2, and you should remember that the difference was only the terms of partial derivatives multiplied by du and dv. So this vector comes out to be, as you can see on your slides, the first coordinate is partial derivative of phi with respect to u multiplied by du, and second coordinate is partial derivative of psi with respect to u multiplied by du. Similarly, the other vector, which is from point Q1 to Q3, is obtained by subtracting the coordinates of point Q1 from coordinates of point Q3, and this vector comes out to be partial derivative of phi with respect to v multiplied by dv and partial derivative of psi with respect to v multiplied by dv. Now that you have coordinates of your two vectors, you can find the cross product by any mean that you know, and I prefer the method of determinant, where you put first coordinate of first vector on top left corner, the second coordinate of first vector on top right corner, and first coordinate of second vector on bottom left, and second coordinate of second vector on bottom right corner. You have this determinant, multiply them, subtract the multiplication of the other two components, and you get your determinant. And this determinant can be a positive number or negative number depending on the order in which you use the first or second vector. If you find cross product of A into B, it can come out positive, but if you find cross product of B into A, it will be the same number but with a minus sign. But we want to find the area of the parallelogram, and area is a positive number, so you take the magnitude of the evaluation of that determinant. So you evaluate the determinant and then take magnitude of that. This determinant, where the first coordinate is partial derivative of phi with respect to u, and second coordinate is partial derivative of psi with respect to u, and the third coordinate is partial derivative of phi with respect to v, and fourth coordinate is partial derivative of psi with respect to v, has a special name. It's called Jacobian of this transformation. The transformation from uv plane to xy plane involving these transforming functions phi and psi. When you have this determinant where partial derivatives are written in four corners, this determinant is called Jacobian, and the magnitude of that Jacobian is the area of that parallelogram, and you multiply the area of that parallelogram with the joint PDF of x and y to get the probability of the same event. Remember, we assumed one-to-one correspondence between events on uv plane and events on xy plane. So if you equate the two probabilities, the probability of that event on uv plane was value of joint PDF of u and v at point P1 multiplied by the area of that region, which was du into dv. And the probability of the same event on xy plane is the value of a joint probability of x and y on point Q1 multiplied by magnitude of Jacobian of that transformation multiplied by du and dv. So if you cancel du and dv, it's easy to see how the two joint PDFs, joint PDF of x and y and joint PDF of u and v are related. If you want to find the joint PDF of u and v, all you have to do is find joint PDF of x and y, and instead of x and y, put the reverse mapped expressions which solve x and y in terms of u and v, and multiply it with the magnitude of Jacobian of the transformation involving phi and psi, and that Jacobian has four partial derivatives: partial derivative of phi with respect to u, partial derivative of psi with respect to u, partial derivative of phi with respect to v, and partial derivative of psi with respect to v. So the two joint PDFs are related to each other with a Jacobian and change of variables solved through the reverse transformations phi and psi. Let's apply this methodology to an example, and we are going to take the example we have been working with since many lectures. The example of two televisions, their underlying random variables which are their service times, and their derived random variables which are sums and differences and ratios of service times. So the first example is where u is equal to y minus x and v is equal to x plus y. So these are g and h. So g of x comma y is y minus x, which gives us u, and h of x comma y is x plus y, which gives us v. So if we solve these equations and try to find the relationship of x, y, u and v in such a way that we have an expression for x in terms of u and v, an expression for y also in terms of u and v. We have our reverse transformations which are phi and psi. So it's very simple. Both transformations y minus x and x plus y are linear. Solve them and you get your reverse transformations phi as shown on your screen to be v minus u whole divided by 2, which gives us value of x. Similarly, psi, another transformation, takes u and v and applies this formula u plus v whole divided by 2 to give us y. So when you have these reverse transformations where you can replace x with a function of u and v, replace y with a function of u and v, all you need to do is find Jacobian of these phi and psi, the reverse transformations. So you take partial derivatives with respect to u and v and they come out to be minus half, half, half and half. It's so easy, you can easily find that out. And these partial derivatives, when put in a determinant and the determinant is evolved, they give you a value of minus half. And the magnitude of minus half is simply half. So if you want to find the joint PDF of u and v, then it is related to joint PDF of x and y and then multiplied by this Jacobian, actually magnitude of the Jacobian, which is simply half, but in the joint PDF of x and y, x will be replaced with v minus u by 2 and y will be replaced with v plus u whole divided by 2. You can see on your screen that after this replacement, you get an expression of joint PDF of u and v, which is 0.0025 e raised to power u over 40 times e raised to power minus 3v over 40. This is exactly the same joint PDF that we obtained when we worked this problem through finding the joint CDF of u and v, taking double partial derivatives to get to the joint PDF of u and v. This procedure gives us directly the joint PDF of u and v. However, it does not tell us one thing: the domain over which this joint PDF of u and v is defined. You have to use these transformations g, h, phi and psi to transform the domain of x and y into domain of u and v to make sure that you take proper points u and v to find probabilities of interesting events involving u and v. Let's take our next example where we were interested in finding the joint behavior of total service time and the ratio of two service times. In that case, our u was defined as y over x. So g as a function of x and y was y over x. If we want to solve this g and h to get our phi and psi, we can do that, but the expressions are more complicated because this g is not a linear function, it's a non-linear function, it's a ratio of two values of two random variables. So u is y over x, a non-linear function, but still you can solve for the reverse mappings phi and psi, which you can see on your screen come out to be phi is v over 1 plus u and psi to be uv divided by 1 plus u. So these are slightly more complicated expressions of u and v. If you want to find the Jacobian which involves these reverse mappings phi and psi, you have to take partial derivatives of these phi and psi with respect to u and v. And because there is a factor of 1 plus u below, the partial derivatives are going to be complicated expressions. But you can think carefully and see that this Jacobian of transformation relates how a rectangular region becomes a parallelogram region, and then it gives you the area of that parallelogram. So if a rectangular region on UV plane becomes a parallelogram on XY plane through Jacobian of the transformations involving phi and psi, then a rectangular region on XY plane should become a parallelogram on UV plane through the Jacobian, which involves G and H. In this example, G and H are much simpler functions, so we are going to take partial derivatives of these functions. This is also a Jacobian, and this is going to be used in this question, with one difference, that previously joint PDF of U and V was joint PDF of X and Y multiplied by the Jacobian which involved phi and psi. Now the joint PDF of U and V will be equal to joint PDF of X and Y divided by the Jacobian which involved G and H. And we already have the reverse mapping functions of phi and psi. Combining everything together, for this example, you can see on your screen that the joint PDF of U and V, where U is the ratio of two service times, V is sum of two service times, comes out to be 0.005 multiplied by V over 1 plus U whole square e raised to power minus something, a complicated expression that you can easily see in your notes or on your screen. So with this we run out of time, but we have covered substantial ground today. We have formulated a methodology to find the joint PDF of U and V to derived random variables from joint PDF of X and Y to underlying random variables by directly manipulating small regions and events represented by those small regions, and through extension of Taylor series to get the area of a small rectangular region in one plane related to area of a parallelogram in another plane through the Jacobian of that transformation. That is a lot of things to understand, absorb and use. I hope you will work hard to understand these concepts thoroughly and be able to apply these concepts to solve problems related to pairs of derived random variables. We'll continue this discussion in next lecture. Till then, I wish you the best. Thank you. Khuda Hafiz.